I don't know. Did you see Gabriele, Luca?
Oh, no, I didn't see them downstairs.
I mean, I think you can start.
Is there a good reference for this word for?
Actually, I was going to ask you.
Okay, so I was saying that starting from the ground state of this Hamiltonian, basically when you are at this line here, we're looking for a protocol where we didn't have to make measurements. Sorry, we didn't have to use some ancillary degrees of freedom, and we wanted to perform with measurements. So, as I said, the possibility is to measure a subset of sites with some periodicity structure. And the reason for which this corresponds to doing a weak measurement is the following. So we can rewrite the post-measurement state in this form. I always neglect the normalization, but keep in mind that the wave function must be normalized. And this is the...
Can you say again what this N was?
N is the measurement outcome. So for instance, for this case, I would call it N to J equal to 0. And this defines a vector N. Because I just measure the even sites and the post-select 0. And this H of N is basically the collection of all the K sites that I'm measuring. Okay. And so in the limit beta going to infinity, this Hamiltonian here, this here, beta going to infinity, becomes product from A to 1 to K of N I K and I. So it's really a projector. No? When beta goes to infinity, I'm projecting into this configuration here, for instance. And okay, so what is the, let's say, underlying theory description of this, or better, of this? In order to derive it, oh, sorry, I was not using the hat. Well, in principle, I should always use the hat. But then it takes a lot of time to use the hat, but think that these are our operators. I mean, in principle, here it would be useful to use the hat because this is the outcome. But maybe think that there are hats. Okay, so what is the let's say, what is the action associated, the defect line action associated to this post-measurement operator? And in order to write down the action, basically what we have to do is invert this relationship.
What is I indexing? I don't know. It's NIA.
Right. So because we have a set of indices, let's say I1, I2, Ik. This is the set of indices that we are measuring.
So the even ones.
In this case, the even ones.
Okay.
With the measurement outcome NI1, NI2, and Ik. These are the notations. So I measure, so in this case, here, but in that example, I will measure the even case and with measurement outcome 0, 0. So now, if we use this dictionary here, we can basically invert them. And what we find is that the defect line action that one gets takes the form, so delta S takes the form of beta integral dx. Then we have a sigma x equal 0 plus a epsilon x equal 0. And up to some limit. So now the question is, how and what is the value of this a sigma and the epsilon, and how they are related to the measurement pattern that we have. And here is where the symmetries play an important role. So maybe what can I raise? I can erase it this time. Okay, so if our measurement is breaks, so if let's say NI1 and IK reserves a translation on an odd number of sites and or reflection, one reflection, then a sigma must be 0. So, for instance, take a measurement with N3J equal to 0. It means that you have a system here, and then either this, and this. And they get 0. Okay, we don't have to be. Okay. So now the unit cell contains an odd number of sites, no? Because we have a unit cell of 3 sites. So this means that these measurements here preserves the translation symmetry under a unit cell of 3 sites. Now, since sigma is odd under this kind of symmetry, it means that it cannot appear in this defect line action because it's not compatible with the symmetry that we are preserving. And so a sigma would be equal to 0. Otherwise, a sigma would be different from 0. But then at that point, both for easing or critical easing, the scaling dimension of sigma was larger than the scaling dimension of epsilon. No, because so for easing, delta sigma was 1/8, and for critical easing, delta sigma was 3/40, sorry, 3/80. While delta epsilon was 1 for easing and 1/5 for critical easing. So since this operator is more relevant than this, basically this is the one that dominates. So you can see that it's all a game of symmetries, basically. When when we perform a measurement that preserves like the translational symmetry on an odd number of unit cells and or the reflection symmetry, by symmetry sigma cannot appear because sigma is odd under these symmetries, and so A sigma will be 0. On the other hand, A sigma will be different from 0. So for instance, n to this measurement outcome, n to j equals 0, that we said before, doesn't preserve one of these two symmetries, and so A sigma is different from 0, and indeed we get the defect line with the sigma perturbation, which is compatible with the fact that we find this power law decay, that is exactly what we predicted yesterday from E sigma. Like in the presence of this defect line yesterday, we saw that this was the result.
But these coefficients are there because this is just the most general form.
Yeah.
Okay.
Yeah, because I mean, actually, here there is always a coefficient, no? Also for easy, when you write down the dictionary, it's like we can fix the scaling and this fixes the operator, but we cannot fix the prefactor. It's like trying to predict analytically the like if we have something that scales as 1 over j minus k to some power, and there is a prefactor here, no? That prefactor depends on this, and it's not non-universal. I mean, in principle, it could also depend on the site, j, but since we're assuming translational invariance. So now let me highlight what are the advantages of this method. First of all, basically, just with changing the measurement outcomes and changing the symmetry that this measurement outcome have, we can realize both a sigma or an epsilon perturbation. So this is the first thing that we have. The second thing is that so this is something that I will explain more in details tomorrow in the context of projective ensembles. But in general, like in a lab, what people do is they take snapshot of their system. So taking snapshot means that suppose that they want to compute correlation function, they will like take some pictures of all the positions of these sites, no? So they have a string of they have a set of strings, and well, these are some zeros and ones. So, for instance, let me try. Let me try to make an example. Like suppose that I have 4 sites in my experiment, and I take some snapshot where I measure. These are random numbers, no? Then I want to compute the correlation function on the. I want to compute the correlation function on the last site. So what I have to do is I average, no, the outcome along the 4th side. This is how people compute correlation function in the experiment, basically. Now, we have already done an experiment where they were able to prepare the ground state of this Hamiltonian and they were computing correlation function. So we have already access to this set of string of outcomes. Now, what we have to do on top of this is just taking, for instance, the strings where all the second sites are 0. So it means that here you would take these and these and these. And then you would average over this subset of sites. So basically, we would average over these. Because this one that doesn't have to j equal 0. So this way of performing weak measurement has, first of all, the advantage that, I mean, the experimental overhead compared to what has been already done is very low. It was just has to restrict on a specific subset of students. Then, as I said, like just changing the measurement outcome, we can realize both types of measurements, like Z or X. And then the third thing that I would like to comment is the fact that the post-selection probability for these measurement outcomes are not so bad. What do I mean? So if I define by P of n the post-selection probability of a given measurement outcome, so we found that this decays as e to the minus, let's say, 8. So K is the fraction of sites that we measure. So let's say small r over capital L. And A is a sort of correlation length. So basically, in order to find a probability which is not too small, it means that A must be a small number. So we found that, of course, all the post-selection probabilities for this outcome was exponentially decaying in system size, which is what you would expect. However, this A here was very, very low, like in the sense that for order 30 sites, we could find something which was a probability of also 20%. So something very, very high. And for me, like, I think the main reason is that we are working with a blockade regime. Let's do a simple example. Suppose that rather than selecting 0 here, I would have selected 1 on all the sides. Now, since we are working the blockade regime, there is only one configuration in the hyperspace which is compatible with this measurement outcome, which is the one where we have 0 on all the sides. Now, because otherwise, all the other configurations are not allowed in this restricted hyperspace. So for sure, the very high post-selection probability is due to the blockade regime. Then the second motivation is that, we are at the critical point, and the critical point, and we are at the critical point, and we are selecting for this space, where we have, sorry, for this outcome, where we have 0. And this is somehow accommodates both the disorder and the charge density wave configuration, which are the configurations with the highest weight in the critical state. So accommodates both disorder and charge density weight. Yeah, moreover, you see that if we lower, let's say, the density of sites, like for instance, we consider n for j equals 0, like we measure on every 4 sites, we get the same result, and this post-selection probability increases. And then also, like for every outcome, for instance, here I can choose n to j equals 0 or n to j plus 1 equals 0. Like I can also measure on the odd sides. The physics is the same. And something else that we observed that I think also enhances a lot this past selection probability is the conditional probability, the behavior of the conditional probability, meaning the probability that at a given site k, you measure 0, for instance, given that you have measured 0 up to that site. So if we plot this conditional probability for that outcome there, we call it the P of k, so the probability that I measure at the site k 0, given that I have 0 up to the site k minus 1, so in this case 2k minus 2, was had this behavior. So after really a few set of sites, we found a very strong saturation to 1, meaning that it's very likely that if you have measured 0 up to the first site, in the first sites, then you would get 0 also on the remaining sites. So if you want, there are a lot of nice ingredients here that make this roadmap very promising to extract some measurement after criticality. One is the fact that we have already the data. The second is the fact that this post-selection probability is very high. So the current status is that we are trying to match the behavior of the correlation function before measurements, before any post-selection, for the raw data that we have, like to first check how it compares with the original critical leaving case and whether there is or not a good agreement. And then the plan is to make the study for this measurement after criticality.
You also get the area law entanglement here that we saw last time.
Exactly. This we were able to check numerically. In the experiment, I don't know how to extract the entanglement entropy.
Yeah, okay.
Yeah, no, the physics is exactly the same. So, for instance, if you measure, like for instance, on every 3 sites, we found a power law decay which was close to 1, and the SLD, which was compatible with the next interpretation that we described yesterday for Parisian.
But there you get the log entanglement.
With the log, yes. Yeah, because
The physics needs to be the same, right?
exactly.
It's
Yes.
interesting to me that it makes such a difference. And if you switch from an even number of sites to odd, it would just switch this size of the cell, right? So if I have an odd number of sites, now the even size, if I measured on all the even ones, would lead to the log law, right?
Wait, if you measure on every 3 sites, or if you just measure on the
No,
odd sites?
because this is dependent on the number of sites, if you have an even number or odd number.
Exactly, yes.
Okay, if you go from, let's say instead of 20, I have 21, it changes these cells, no? Or I'm seeing wrong because it changes that symmetry of the sigma field.
So you mean that I add the new set, I add the new site here,
Mm-hmm.
and then how do I change the measurement?
No, just the same measurement. Because
Uh,
doesn't it change the symmetry of the sigma field from being like odd translation to even translation?
okay, so in the numerics that we have done, we were always considering even systems.
Mm-hmm.
And all the checks that we have done were done in such a way that we were, like for instance, if we measure on every 3 sites, we were choosing a system size which was a multiple of 2 and 3.
Okay. Yeah.
I don't think that adding just a further site would change the physics because it's like, I mean, it's at most something local that is happening.
But doesn't it change the symmetry of the sigma field? That's what I'm a bit confused because you said.
Right, like we have to introduce another symmetry operator which is rather than bond reflection, site reflection.
Okay.
But then,
yeah.
Yeah, so if you have an odd number of sites, the relevant symmetries are still, let's say, translation and deflection, just that it's not reflection around the bond, but it's reflection around the site.
So did you check like for random measurements or just sites? Of course, then there is not this nice translation invariance.
Yeah, so we try to do that. But I mean, it's a bit late in the case of using. It's hard to say if there is some power law decay, what is the leading power law decay that one find in that case.
Because there is this work, I think, by Siro there in France that they do these projective measurements, but randomly on an Ising critical state, and it always preserves this log law on average. I don't know if you've seen.
But this is in time.
No, without time, just starting from the critical, and you measure with a certain probability, I don't know, for a number of sites, but you measure projectively. And it doesn't destroy this entanglement. That's why I thought it was very curious that if you choose only the even ones, it destroys this log L.
No, I don't know this word. But when they were measuring, so they were considering easing?
Yes, easing, but not the anti-ferromagnetic, the ferromagnetic. I'm not sure if it would make a big difference at criticality, and they say they have a probability P of measuring each site, and then they measure, and it can be 0, 1, or whatever, but they can both select as well, and it doesn't destroy the log law entanglement. I don't know about correlations, they didn't.
No, right. So if you have easing in the ferromagnetic case, and I think they were measuring X, to say that it doesn't.
No, Z.
Yeah, but Z. I mean, Z for them was the transverse field? Or?
Yeah, in the transverse field.
Yeah, okay, so if they were, then I agree. Like, if you have easing in the ferromagnetic case and you measure the transverse field, say, with some probability, then the effective description would be as having an epsilon perturbation.
Okay.
And so you don't destroy the because the point is, when you do a measurement, what is the defect line? Like, it's much easier, even though you do some projective measurement, to think in terms of weak measurement. So there, the weakness comes from the fact that on every site you have a probability of measuring it or not, and with some outcome. So then, once you run your protocol, you have to ask, okay, what is the corresponding defect line that I have? So in their case, the corresponding defect line that they would have is an epsilon. And if we have an epsilon in using this would be marginal. And so you would preserve the log F.
Okay.
Do you have any comments, questions? These, maybe then I think it's, I mean, to finish this part about the measurement of the criticality, such that tomorrow we go to start more we study more the projective ensemble. I would like to,
Maybe a general question. Like,
yes.
yesterday you also started saying that one of the point is that you want to measure particular states of many body systems. But I mean, I guess all the people choose these critical states because there is this CFT language, right? But like, because since you said before that this model is basically the PXP model, which has like scarce states, right? So one can perform measurements also in these particular states. So,
You mean on the scars?
yeah. So, but I don't know if there is a reason to do that or there is a field theory language for that, but I mean, maybe it doesn't make sense.
Scars, I think, are like, if they are described by field theory, I don't know, but maybe they would be described by a quantum field theory, like a gap field theory, right? Because they have area law entanglement, I think, and I guess correlations would decay exponentially. So what is the point? That if you have a correlation function that, for instance, decay exponentially, like the length scale is already non-universal.
Right.
So once you do measurement, you go from something which is non-universal to something else which is, again, non-universal. So it's like...
So let's say, let me ask the other way. Are critical states the only kind of states that are interesting to measure, or maybe there is something else?
No, I'm sure that there is something else. Just that like with this kind of local measurement where you don't change the phase. Like, okay, so for instance, the example that you were doing with these long range measurements, no? There actually you can ask, okay, I do a phase diagram, I have the magnetic field, where here I have my critical states, and then I turn on my measurement, and I can ask, is there a way to start from a state which is trivial and perform a measurement such that I end up into a non-trivial phase, like into a topological phase. So like I can ask whether there is a phase diagram like this. So I start from a state which is trivial, I do measurement, and then there is a critical value of my measurement, after which I go into a, so let's say this is a topological phase, and this is a trivial phase. You can ask these kind of questions, yes. Just that to have this non-trivial transition, you need to perform measurements which are more complicated than the one that I'm doing now. Like with the single site measurements or with local measurements, I won't change the phase of the system where I am.
But you consider only this single site measurement because that's what they can do experimentally, or they can also measure like two sites together, like they can do non-local measurements?
And I think if you have gates, then you can do also non-local measurements. No? You can engineer something at least by local. Of course, less the less is local, the more it's difficult to implement. In this kind of experiment with Reaper, what they do is single site measurements. They just measure in the occupation number basis, and that's it. I think that if one would be able to do this more digitally, then there is more room. But then it's the problem of preparing digitally a critical system. I mean, there are proposals to do it, but I haven't seen anyone doing it. So the answer is, I think with local measurements, the most interesting ones are the critical ones. But maybe, I mean, if you engineer some measurement which is a bit more exotic, let's say, not exotic, like that are not these ones that I was discussing these days, then I think it's interesting, especially if you want to tune from one phase to the other. And okay. Are you ready? Yeah, so basically yesterday we have introduced this concept of measurement alpha criticality, and I tried to show what happens for the easing model, how one can describe it in terms of CFT, of conformal field theory. Then today, okay, we have briefly seen what happens for typical outcomes, and then I've done these examples with the Rydberg atoms, where I tried to convince you that actually Rydberg, like, there is a way to implement quick measurements also without considering degrees of freedom, and yeah, we have identified a protocol that in principle should allow us to get something of measurement alter criticality with the data without a large experimental overhead, and also with a not too bad the post-selection probability. Now, the question is, are there other ways to extract signatures of this measurement alter criticality, like rather than just looking at individual outcomes? And this is actually something which is already done a lot in the context of measurement-induced phase transition, meaning averaging over all the possible measurement outcomes. So the first naive guess that one would do is, okay, let's try to look at quantities like sum over n, Pn, psi of n, O, where O is a generic operator, J, psi n. Now, this operator here, so if we denote as psi n, like e to the beta, sum over j, okay, let me call this aj and this aj. Psi divided by square root of Pn. So if we plug this definition here, what happens? The Pn basically simplifies between denominator and numerator, because we have one square root of Pn coming from the bra, one coming from the ket, and this will simplify with Pn. So we would have sum over n, psi, e to the beta, sum over j, j, e to the beta, sum over j prime or j prime. Sorry. And if we commute these two objects and we sum over all the possible here I want to do percentage. So then we sum over all the possible measurement outcome due to the completeness relation that Krauss operators must satisfy. This would give back basically psi aj. So the pristine correlation function. And this is very boring, like we don't like this. Because we don't learn anything new about the fact that we are doing measurement. So this is really like washing out all the measurements that we have done. And this it's like, I think very similar. It happens the same in the context of measurement-induced phase transition, which is then why people decided to look at the average of the entanglement entropy. So quantities that are non-linear in the density matrix. That's the idea. So the usual candidates of quantities that one can look at are the following. So suppose that suppose that you want to look at this quantity here. From the cyan. Minus. So basically, I'm averaging the connected correlator. So the first step is trivial, no? Because as I said, like this is linear in the density matrix, so it would just give the pristine correlation function. However, here there is also this step. So now the non-triviality of this average comes from the fact that we have a product of two-point correlation functions. Two single-point correlation function. And so, for instance, already the trick that we did before, no, like in simplifying the normalization of the state of the probability doesn't apply here because we have 1 over Pn squared, while here we have Pn. So this quantity is non-trivial. And so more in general, one can think that, let's say, a non-trivial, non-trivial correlator that one can extract takes the form when sum over n Pm, and then we get the product integrated from 1 to n of psi of n for j psi of n. Okay, so how can we rewrite it? Now, for simplicity, just writing this as mj, where mj is the measurement operator, acting on depending on the measurement outcome, acting on psi, divided by Pm. So if we plug this definition of the post-measurement wave function here, what we get is sum over m, Pm to the power of 1 minus n, where this minus n comes from the fact that we have n factors of Pm in the denominator. And then we have product of j, sorry, and dagger. I keep calling this O, but this should be A because just not to confuse with the measurement here. They can be the same, but they don't have to be the same. Here I'm just writing this expectation value using the fact that psi of m takes this form. However, the nice thing of this rewriting is that it makes clear somehow that we can use what is called as a replica trick. What is this replica trick? So the idea is to introduce a set of replicas, let me call them R, such that basically in the limit of r going to 1, if we have t to the power of r minus n, this is exactly Pn to the power of 1 minus n. This is
Sorry, just to understand, are we looking for a smart way to write this second term, right?
exactly.
Okay.
Yes. Yes, and the smart way to write this second term is in terms of replicas.
Okay.
I mean, it's a rewriting. Then sometimes the rewriting can help. Sometimes you don't know, not even how to compute the rewriting. But for this correlator here, there is some smart way to go on. And yeah, by the way, this replica, just to give some context, this replica trick in the context of disorder system was introduced mainly in the literature of disorder system or spin glasses by Parisi, Giorgio Parisi, who won the Nobel Prize a few years ago. So it's not a secret trick. It's no, in the sense that it has been explored a lot in the context of disorder systems. Like what changes between disorder systems and measure is the presence of this P of n. Like usually when you do measurement, you average your quantities according to the Born probability, like the probability of getting that specific measurement outcome. While when you perform the average over disorder realizations, you don't average over the probability of getting, usually you don't average over the probability of getting that specific realization. So like maybe if you have seen something in the literature of the disorder system, then the replica case takes the limit of r going to 0 rather than r going to 1. Just because we have this Born probability factor. Just because there are people from Rome, like I have in mind that if there is someone from Rome, then Parisi must be. Okay, so this means that if I want to rewrite this in the replica limit, this becomes the limit when r goes to 1. Sum over n, Pn, r minus n, and then product over j, and then we have psi, and bucket, aj, and n. Okay. And also something that I want to mention is that when n is 1, basically this factor cancels, and this is not by chance, but this is consistent with the fact that if n is 1, we get a quantity which is linear in the correlation function, and so we get back to the, let's say, pristine correlator. So nothing interesting happens. Okay, so now keep in mind that we can use this replica trick. Let's try to find a smart way to rewriting at least this average of a connected correlation function, where basically we have n equal to 2, but we have these two disconnected terms. Okay. So if we just look at this term here, suppose that I introduce so a set of replicas, and the idea is the following. So each of these correlators here basically correspond to correlation functions that are introduced on two different replicas. So yeah, like the natural guess that one would do is So these two terms here basically can be computed as a two-point correlation function of an operator. I was using of x, using this. An operator of x living on one replica, and an operator of y living on another replica. So this correlation function is computed on the replicative theory with A different from B. While this quantity here, which is more trivial, would correspond to compute a correlation function Ox or y now on the same replica in this replicative theory. So basically, we can write the correspondence between these. So if you want to write down this object here in the replicated theory, basically this would correspond to a correlation function between two operators, Ox and Oy, which live in the same replica, minus the correlator Ox Oy living in different replicas. So with A different from B. And this choice of replicas is arbitrary. Like here I could have chosen BB. It doesn't matter. And the important thing is that they are computed this one in different replicas is because I mean, all these replicas are coupled by these measurements here. Right, so it's like if I have, suppose that I have two replicas, so I have my first x tau space time, then I introduce my second replica, and these two replicas are actually, let's say, coupled. It's like if, let's see if I can draw it. Okay, so you have your first replica, which is this sheet here, and then you have the second replica, okay, this one here, and the two replicas are coupled at time equals 0, where we have done the measurement. So these two replicas are not independent. That's why it's interesting. I mean, the interesting thing is really this object, now where you have two fields living on two different replicas. With this A different from B. And this term is non-trivial because the two replicas are coupled by the measurement. So maybe we can try to do an example of a measurement which is easy to deal with, where we can extract, I mean, we can understand how to compute this quantity. In general, as far as I know, for instance, for easing, these replicated quantities haven't computed. Like for measurement alter criticality, this quantity here haven't been computed, and I also don't know how to compute it. It's really, let's say, state of the art problem. But I will try to make an example where this replicated quantity for a specific measurement in a specific theory can be. Okay. So, suppose that we have a measurement operator, M of n, which is proportional to the exponential of integral dx integral 2 integral dx M of x minus x, which is an operator. So I have a Gaussian measurement. Okay. So a Gaussian cross product. And the probability distribution, Q of m, can be written in the particular formalism as an integral over some scalar field, phi, e to the minus s of beta, which is a functional of phi and n, where is s of beta phi n is the effective action of the unmeasured state of this critical field phi plus e to the 2 integral dx M of x minus x squared. So I'm choosing a cross operator such that my measurement is Gaussian, and I'm rewriting the post-selection probability, the probability of getting a specific measurement outcome as as we've seen yesterday, no? As the unmeasured critical theory plus a defect line, where now my defect line is Gaussian. So what can we do? If we replicate our theory R times, then we can compute the partition function, which is sum over n, Pn to the power of R, which is basically the integral of the product of all the replicas from 1 to R, d phi of A, e to the minus s of R of phi A, okay, where basically in this replicated action, what we can do is, this action depends on both phi and m, but m appears in this Gaussian form. So what we can do is integrate out the effect of the measurement, because it's a Gaussian integral, such that I can get an effective action that depends only on the field phi of A. So it is a replicated action. Basically depends on sum over A, S of phi A. Okay, so the action term by term. And then if we are performed, it's a functional integral over the measurement outcome. We get e to the 2 integral dx sum of the I and b from 1 to R delta A B minus 1 over R x A x B.
And then you always take the limit R to 1.
At the end. so this is the, I mean, there are different replicas, different replicated quantities that you can compute. Like, in principle, already computing this object here as a function of R contains the trivial information about the measurement because it's non-linear, because it's not in the limit R going to 1, this quantity itself